Welcome to the 40th lecture on computational mathematics with Sage Math. In this lecture, we will look at least square problems as an application to linear algebra. We have already seen how to solve least square problems using calculus. So, let us first start with a problem. So, suppose you have a random 6 cross 4 matrix whose entries are, let us say, integer from -10 to 10. Then A can be thought of as a linear map from R4 to R6. Now suppose there is a vector B in the codomain which is 1, 2, 3, 4, 5, 6. Now the question is, does B lie in this image of A, that is column space of A? If it lies, that is same as saying the Ax equal to B has a solution. However, if it does not lie in the image space of A, in case B does not lie in the image space of A, then we can ask for what is the point x star, let us say in R4, such that the image of x star under A, that is Ax star, is at the smallest distance from B in the codomain. Okay. Now this such a x star is known as least square solution of this system of linear equation Ax equal to B. Now you can note that this Ax star is actually nothing but the orthogonal projection of B onto the image space of A. So that is what we will obtain. We will obtain the least square solution as an orthogonal projection of B onto image space of A. Okay. So let us see what we are saying here. So in this case we have a system of m linear equations in n variables, and let us say that is Ax equal to B. If x equal to alpha is a solution of Ax equal to B, then B lies in the image space of A, right. And the least square solution of Ax equal to B is x star, which minimizes the distance of Ax from B for all x. This is the minimization problem. That is how we have seen as a solution to this problem in calculus. And note that if x star is a least square solution of Ax least square solution, then Ax star is the orthogonal projection of B onto image space of A. That is what I already said. Okay. Now suppose this m is bigger than equal to n, that is you have more equations than the number of variables. And let us assume that A is of full rank, that means rank of A will be n here. In this case, solving this Ax equal to B or finding the least square solution of this Ax equal to B is same as you just multiply both sides Ax equal to B, both sides by A transpose. So what you will get, A transpose Ax is equal to A transpose B. Now this is what is called normal equation of this least square problem. Now least square solution of Ax equal to B is nothing but a solution of this normal equation A transpose Ax is equal to A transpose B. Now this, since A is of full rank, that is rank of A is n, A transpose A, which is n by n matrix, will be invertible matrix, and hence the inverse will exist, right. So finding least square solution of X equal to B is nothing but solving this normal equation for X, right. One can also obtain this least square solution, namely X star, as a solution to this Ax equal to B, but since A may not be invertible matrix, what we need to do is we need to find the generalized inverse of A and then multiply by B. Notice that if A is invertible, the solution X is A inverse B, but even if A is not invertible, then we can find its generalized inverse. We will look at this how we can solve this in using singular value decomposition, but Sage also has an inbuilt function to find generalized inverse. So in this case, what will you get? You will get the least square solution X star as generalized inverse of A times B. This is how we denote generalized inverse of A. So now let us look at how we can solve this problem which we have stated. Right. So let us start with m and n is equal as 4 and 6 and define a random matrix over integers whose entries are coming from -10 to 10. Right. Now let us see what this matrix is. So this is how this matrix looks like, and next let us define a vector B which is 1, 2, 3, 4, 5, 6. Now we can ask whether B lies in the image space of A. So how do you check? You can define, let us say W is equal to A dot image, which is same as saying column space of A. Now we can check whether B in W, whether B in W. The answer is not true. So B does not lie in W. So now then we can ask for what is the least square solution of this Ax equal to B. Now let us define x as variable x0, x1, x2, x3, x4, x5. So you can check what is this x here, x0, x1, x2, x3. Since m is 4, this is x0, x1, x2, x3. We have seen this earlier. Now let us define capital X as vector small x. So capital X is going to be column vector x0, x1, x2, x3, x4. Now if you recall, in calculus we solve this problem. So first we define f as sum of the error squares, and error in this case is nothing but Ax minus B, Ax minus B. So for any x, x1, x2, x3, for any x, x0, x1, x2, x3, Ax is in the image and its error is going to be Ax minus B, and then find the sum of the error square, that is just look at the ith coordinate of this Ax minus B. This will be a column vector. Look at this ith coordinate of this. This is going to be the error square, and they take the error square and take the sum, that is your f. So f is going to be function of x0, x1, x2, x3, and we want to minimize this function. So in calculus, how did we do? Let us quickly do that. We obtain the gradient of f with respect to x0, x1, x2, x3, and this is what we get, and then we solve this for each coordinate of the gradient should be equal to 0. That is the critical point. And when you solve this for x, the solution is going to be given by, let us just wait, it is still, yeah. So x naught is this one, x1 is this, x2 is this, x3 is this. So this is how we have already obtained using calculus. Now except that there in calculus we wrote this as each coordinate. Here we are writing this as a matrix, as a distance from B to Ax, right. Now so in this case, if you want to print the solution as a decimal value, this is what you get, right. Next let us see how we can obtain using okay. So the point which is closest to B is A star x1, where x1 is this solution vector or the least square solution of Ax equal to B, right. Next this point Ax1, which we obtained using calculus, is nothing but orthogonal projection of B onto image space of A. So how does one find orthogonal projection of B onto image space of A? We have already seen that this is nothing but take A transpose A, the inverse of this, and then multiply by A transpose B. So that's your that is your the point x2, which is same as this you have obtained in this using calculus. Now multiply this by Ax2, multiply x2 by Ax2, this is what you get as the least square solution. So we have seen that orthogonal projection of B onto subspace W, which is obtained by the image space of column vectors of basis of W is given by A into A transpose A inverse times A transpose B, and that is what we have got. So, least square solution can be thought of as an application to this orthogonal projection and as an application to linear algebra, right. Now, this again we have seen that you can fit a curve to a given set of points in the plane, or also fit some kind of let us say plane in the space, and this can be generalized. So, if you have to find, let us say, best fit quadratic y equal to a plus bx plus cx square to a given set of points xi yi, I going from 1 to n, then this problem, in this problem we define what is the sum of the error square as a function of a b c, and this is what we got. So, this is summation yi minus a plus bxi plus cxi square, the whole square of this, that is the error of any point on this curve from this yi, and this can be expressed as matrix norm of Ax minus b, where what is capital A? Capital A is the column vector 1 1 1, and the next column is x1 x2 x3 up to xn, the next column is x1 square x2 square x3 square up to xn square. So, this, and then b is y1 y2 yn. So, if you take A, and capital X is A B C. So, if you take Ax, what will you get? Ax, the first entry of Ax will be A plus bx1 plus cx1 square, the second row is going to be A plus bx2 plus cx2 square, and so on, and this minus b, take the first Ax minus b, the norm square is nothing but the first entry in this summand. So, that is how you are converting this best fit problem to a least square problem, that is minimizing this sum of the error square. Okay. So, I am not solve any problem using this, I will just leave it as an exercise. We already know how to obtain this solution of this least square problem, and the solution in this case is going to be x star is going to be A transpose A, the inverse of that into A transpose B, and then you multiply this what you get x star by A, you get the least square solution, right. Okay. This least square solution we can also obtain using QR factorization. So, how do we do that? Let us see, this is what we want to minimize, Ax minus b the whole square. Now, suppose A has QR factorization, A is equal to Q times R, then this norm of Ax minus b whole square is QR minus b the norm square. Now, we know that when since Q is orthogonal matrix, the norm of Qx will be same as norm of x. So, if I take norm of this square, that is same as multiply this whole thing by Q transpose. Q is orthogonal, therefore Q transpose will also be orthogonal. So, therefore, but on the left hand side Q transpose Q is identity. So, this terms reduces to Rx, this should be small x, and minus Q transpose B. So, this let me change this to small x, and let me also add this intermediate step here. So, this is equal to, we are multiplying this by Q transpose, right. So, norm of Ax minus b whole square is same as norm of Q transpose Ax minus b, but A you replace it by QR. So, this is now reduces to norm of Ax minus b whole square reduces to norm of Rx minus Q transpose b the whole square. Now, this least square problem Ax equal to b has reduced to solving Rx is equal to Q transpose B. Now, since R is an upper triangular matrix, this is same as solving this upper triangular system, which is much easier. Now, so here this R you just because R is upper triangular, you split this R as R1 and 0, 0 is a 0 matrix, where R1 is M cross M upper triangular matrix, and Q transpose B you also split as C D, where C is of size M and the D is going to be the size n minus M. Therefore, now norm of x minus b whole square, which is norm of Rx minus Q transpose b whole square, will reduce to R1x minus C the norm square plus norm of D square, but norm D is actually a fixed constant. So, minimizing norm of x minus b whole square is same as saying minimize this R1x minus C whole square. So, the least solution of Ax equal to B is same as least square solution of R1x equal to C. So, let us see how we can solve this. So, again let us take a random matrix 4 cross 6 random matrix and over integer. Now, since we want to find QR factorization, you may have to change the underlying domain from which the entries are taken. So, let us change this ring to RDF, that is extended real field, and then the vector B is again 1 2 3 4 5 6, and then what do? We define QR factorization of a QR is equal to A dot QR. So, we can print what are Q and R. So, this is the two matrices Q and R. It looks slightly in the sense little complicated, but since this is a 4 cross 6 matrix, it will look, it is going out of this place, right. Now, let us define R1. R1 is from R you take out the first M rows and M columns, that is your R1, and then define B1 as Q transpose B, that is B1, and again from B1 you define this as C and D. So, C is take the first M component of B, that is your C. Now, remember we need to solve R1x is equal to C, that is what we need to do. So, what we have to do, we need to solve R1 dot solve right and bracket C. So, that is the solution you are getting. So, that is your x star. Now, if you look at what is the solution using inbuilt function, so it is using this orthogonal projection. So, it is A transpose A inverse of this into A transpose B, and what you get here is same as what you get in this case. So, solving this least square problem is same as solving this system of linear equation R1x is equal to C, and that is since R1 is invertible matrix, solving it is quite easy. You can obtain this using Gaussian elimination method or simply take inverse of R1 multiply it by C, right. So, that is what that is how you can solve this least square problem using QR factorization, except that you need to do this computation of finding QR factorization of A, but once you have done this, then it is quite easy. Okay. So, now let us look at some exercises, just two exercises here. Find least square solution of this system of linear equations, which is 3 equations, this is 5 equations in 3 variables, and B is this vector, and find the best fit quadratic y equal to A plus Bx plus Cx square to a given set of points this. So, this problem is to solve using minimizing norm of Ax minus B whole square, and we have already seen what should be A, what should be X, what should be B in this case. So, that is what you have to use, and once you have A, B and capital X, then the least square solution will be A transpose A, the inverse of that, into A transpose B, that is it. So, you can also instead of quadratic you can try to fit cubic, you can try to fit nth degree polynomial. So, if you want to fit nth degree polynomial, this this matrix A will have first column as all 1 1 1, second column will be x1 x2 xn, third column will be x1 square x2 square x3 square and so on, last column will be x1 to the power n, x to the power n dot 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 xn to the power n. So, this fitting nth degree polynomial to a given set of points in the parabola is quite easy. Similarly, you can also if you have to fit a plane to a given set of points in R3, then plane can be written as z is equal to a plus b x plus c y. So, in this case the matrix A is going to be the first column will be all 1 1 1, second column will be the coefficient of x1 and the third column will be coefficient of second column will be coefficient of x, third column will be coefficient of y. So, if and then the b is going to be the coefficient for z. So, z1 z2 zn will be the column vector will be b, and x1 x2 xn will be the second column of A, y1 y2 yn will be the third column of the matrix A. So, that is how you can solve least square problem and as an application to linear algebra. Okay. There are other methods also to solve this least square problems, but we will not get into all these things. So, thank you very much. We will see you in the next class, and in the next class we will look at singular value decomposition, which is again a concept which has several applications. Thank you.